Welcome back to the Lowdown on Physics. This is screencast number 12 in a series on VCE Physics, Unit 3, Motion in 1 and 2 dimensions. Today we'll be studying satellites. So before we go any further, let's just define what a satellite is, and that's just an object that's in orbit around a larger object. Now we have natural satellites such as Moon around the Earth and planets around the Sun, asteroids around the Sun. Basically, satellites are falling towards the Earth, but they never actually get any closer. So artificial satellites are another type of satellite, and they're something that's not propelled by a rocket, but they're falling around the Earth, so you've only got gravity acting on them. They do have, say, tanks that equip them with a bit of gas to propel them around or adjust their orbit if they need to. Now, Newton proposed this idea 300 years before we first launched our artificial satellites, and the idea is basically like this. It was this thought experiment. So if we had this really tall mountain or tower and we had a cannon on it, that was like the most powerful thing at the time, then if you fire something, it will travel so far. If you fire it faster, then it's going to go further before falling to the Earth. So fire another one even faster, you get further. Fire it even faster, and you keep getting further. Eventually, you can fire it fast enough that the rate it falls towards the Earth will actually match the curve of the Earth and naturally go right round and hit you at the other side after completing a loop of the world. Now, for circular orbits, we can consider or use the concept of circular motion. So we've got a gravitational force that's always acting towards the centre of mass, and hence this will be at the centre of the orbit as well. So we use the equations of centripetal force. Now, the size of the centripetal force is determined by the gravitational field strength at that location. So this comes back to linking in with Newton's law of gravitation. So higher orbits have a smaller or lower gravitational field strength. So there's a lower rate of acceleration. So it's falling towards the Earth slower, which means it will tend to travel slower, having a longer period. Okay, just note that the mass will have no bearing on the mass of the satellite will have no bearing on the speed or the rate at which it's the rate that it's falling towards the Earth. So we look at speed, distance over time, or 2 pi r over t, where t is the period. We look at the acceleration. It's only the mass of the planet that's being orbited that will actually have an effect on the rate that it will fall towards the ground. So we've now introduced another term into our centripetal motion equations, and therefore gravitational force mv squared on r, 4 pi squared r times the mass over t squared, or the universal law of gravitation must equal mg, which is the acceleration due to gravity at that height. So let's have a look at an example. What speed will be required to put a satellite into orbit at a height of 20 kilometers, given the radius of the Earth and the mass of the Earth? So if we look at putting the object into orbit, we've got g equals v squared over r, which is equal to gm over r squared. So therefore, rearranging this equation, we end up with the square root, so multiply by r, the r's will cancel down, we end up with the square root of gm over r, substitute in. At a height of only 20 kilometers above the Earth, it would need to be travelling at 7,900 meters per second. So really, really quick. Gets slower the further up that you are. What's really important here is you've got meters here and kilometres there, so make sure you get your units right when you substitute in. So substitute in, make sure that you can get that answer using your calculator. Okay, second example, we've got Optus B. It's a geostationary satellite. Geostationary means it appears, well, geo's the Earth and it's stationary relative to the Earth. So that tells us about the period of orbit. It's taking about 24 hours to orbit the Earth. So find its orbital radius. So A equals gm over r squared, which equals 4 pi squared r over t squared. So by using two equations and rearranging them, we can manipulate it to find an unknown based on the information we have. We have the mass of a satellite, we have the mass of the Earth, we have the period, and we're after the radius. So by substituting in the information we do have, we can make that calculation. So taking the cube root, there's g, there's the mass of the Earth, there's the period in seconds over the 4 pi squared, and we get a radius of about 4.2 times 10 to the 7 metres, so fairly high up. Find the gravitational field strength. So this is G, which is gm over r squared. We know those values using r that we've just found. So substituting into our equation, I've got G at about 0.224 newtons per kilogram, same as metres per second squared. Find the orbital speed. Well, G equals v squared over r, since G is the same as a. So substituting in, take the square root, you have 3075 metres per second, less than half of what was required at a height of 20 kilometres above the Earth's rate, above the Earth. And finally, find its acceleration. Well, its acceleration, the only acceleration it's experiencing is due to gravity, so it will be the same as the gravitational field strength that we calculated back there, which was, I don't remember now, 0.224 or something like that. Anyway, so that would be it, metres per second squared. I just want to have a look at something now linked into satellites, which is Kepler's laws. Kepler had 3 laws, and this was published before Newton's law of gravitation. So 1, the planets move in elliptical orbits. The Sun is the focal point for that. The line connecting the planets sweeps out equal areas at equal times. The one that's of real interest to us here is that for every planet, the ratio of... Anyway, you can read that. Let's look at that mathematically. So the third law we can actually derive from 2 of our force equations, 4 pi squared rm over t squared and Newton's law of gravitation. Rearranging that, what Kepler was saying is gm over 4 pi squared is constant for anything that we're orbiting. So as long as the objects are orbiting the same mass, this is a constant, is equal to r cubed over t squared. So if you increase the radius, then the period will increase also, and it will stay in that ratio. That is something that's not technically in the course, but put that on your cheat sheet, because I've seen a couple of times what is a more complex question to solve could quickly be solved using that there. So what we're basically saying is for any central body m, anything that's being orbited, r cubed over t squared is the same. So sometimes you'll be given r and t for one planet, you get given r for a different one, find t, or vice versa, given t, find r. So we're saying ratio wise, r cubed of t squared for planet 1 is the same as r cubed over t squared for planet 2. So given 2 values for one planet and 1 for the other, we can find the other unknown. So you need 3 of the 4 unknowns because we've got one equation. As soon as you got that, you can evaluate, rearrange, and solve. So let's have a quick look at an example. We've got r cubed on t squared for the Earth. So we know this constant for the Earth. We know the period of Pluto. Find r for Pluto. So let's substitute in. We've got r cubed on t squared is a constant. It's that constant. So if we multiply the constant by t squared, which is what we've got here, and take the cube root, we can calculate r. So R is 5.895 times 10 to the 12 meters. So this brings us, I guess, to weight and measuring weight. When we talk about, we see satellites that are weightless, what does that actually mean? So we can measure the acceleration of a falling object in an inertial frame of reference, so one that's not undergoing acceleration, so somebody standing on the surface of the Earth. We can measure how quickly it's going to fall, or the rate that its velocity changes as it falls. Or we can measure by looking at the normal reaction force. If it exerts a force, then an equal and opposite force is exerted, and we can measure that force. That's effectively what we do when we use scales. So equal and opposite, Newton's third law. So weightlessness is only something that could happen when we're an infinite distance from any other body. So when we set R to infinity, then we're heading towards 0. Or at a point where all gravitational forces cancel out. So if you were midpoint, or at a 0 point where there was equal and opposite forces acting from different planets, then the net force would be 0, and so you would effectively be weightless. Now, if the measuring instrument was falling, then you're falling at the same rate and no weight force would be observed. Okay, you would not be able to apply a normal reaction force because it's a non-inertial frame of reference. Okay, so does that make sense? If you're both falling, then there's no normal reaction force because you're both accelerating. So classic lift problem. We've got a person standing on a set of scales. They have a weight force. If it's moving at constant velocity or it's stationary, your weight would read normal. There would be equal and opposite reactions. If it's accelerating upwards, then you would have a heavier weight reading. There'd be a greater force pushing you up due to the acceleration of the lift up. If it was accelerating down, like just when it starts moving, then you would have a smaller than normal reaction force. If the elevator cable snapped, both of you were falling down, then you would be weightless. Okay, and that's effectively what's happening to astronauts that are in a satellite. As they fall towards the Earth, both the satellite and them are falling, and so they appear as if they have no weight and are floating around in there because both of them are falling towards the Earth. Of course, they fall at such a rate that they never actually get to the Earth, so they continue in this free fall towards the Earth, around the Earth continually. Alright, that's it. I know that was pretty full on, so I'll see you in class shortly and we'll go through any queries that you have. Cheers.